Good evening, everyone. Welcome to this first problem-solving session for the course Computational Continuum Mechanics. So these sessions will be recorded and will be uploaded on YouTube so that you can access them after the sessions and in case you have any doubts. I will also make the presentation with whatever I write available on a shared Google Drive so that you can go through them. Yeah, so that is just to let you know of it. So we have about 5 attendees, fine. So this course on computational continuum mechanics, I hope you would have had the chance to watch the 2 lecture videos for the first week. And yes, so let me introduce myself first. I'm Naresh. I'm a research scholar, a PhD candidate in the Department of Civil Engineering at IISc. I work in computational solid mechanics. I work in particular in large deformation plasticity of certain kinds of architected materials. So I'm currently in the 4th year. I'm finishing the 4th year of my PhD, and I have some of you know I have offered other courses on NPTEL before this. I have done a structural analysis weekly session before this, and I also did gate sessions. With that, I welcome you all to this. Let us hope this is really productive for everyone who attends. Yes. So, NPTEL has asked us to. You can introduce yourself. What do you work on, and what do you expect to learn from this course? Maybe you can go in the order of order in the display there. So I'm Naresh. I've introduced myself. You can tell about yourself if what is your background so that I can help with. I will know which level to start from. So you can. Yes, maybe. Maybe anything at all you can. What is your background? If so, this is a graduate level course. So if I could know up to which level you're comfortable with, we can start from there so that it is quite. Again, it's just an informal introduction. You can do it. So maybe.
I'm Dharani from Tyagaraja College of Engineering, sir. I'm comfortable with finite element analysis.
Okay.
And solid mechanics and structure analysis.
Okay. Okay. Thank you. Okay. For some reason, this question has made people leave the session. Maybe they're too reserved to tell that. Okay. If you don't have to leave the session, you can also choose not to tell if you're not interested. It's fine. Okay, fine. Let's get started. So this course is on computational continuum mechanics. This is a graduate level course. It assumes only the basics of. You're expected to be strong in mathematics, the engineering mathematics part, and also solid mechanics. These forms the basics. So what we expect to provide from these sessions is, so I will start every session with a quick recap of the concepts covered in that particular week. So then if you have any doubts regarding, if you have any doubts regarding this, the content covered in the week or the assignment questions or the assignments of the previous sessions or anything else at all, anything related to computational continuum mechanics, you are welcome to put them forth in these sessions. I will. So this is there. So this we'll do it every session. I'll start with a quick recap of whatever is covered in the week. And doubt clearing, you can either ask in person. You can directly ask in the session. You can also post it on the Q&A. I will address those also. You can also post it in the Q&A section of the course. So that is actually here. Yeah, you can post it here. Right? You can go to this Q&A section and you can, yeah. So you're recommended to register Nothing, but you just have to join. Okay. Yeah. So this discussion forum for continuum mechanics, this portal is opened by NPTEL itself. You can get into that and then you can post any query you have, any doubts, and I will address them in the session as well as in the answer thing. So we'll start with a recap, then you can ask your doubts. Then we'll also solve some problems that will help you with the assignments. For example, this week, so this session will be focused towards assignment 1. Right, so assignment 1 is due on 7th August. So this is assignment 1. This is due on 7th August. And as you can see, for this week, most of the questions are theory type. So you don't have any problems to solve as it is, but we will solve some problems to get the concepts cleared and also to help with some of the basics. So mostly it is true or false and some kind of it is theoretical. So we can have it. So we'll solve problems. Then what I thought I should also include for a course like computational continuum mechanics is that you should have some coding practice. So we will, because it's a 2-hour session, and if all the assignments have only theory questions and not serious problems, then we may spend some time into uh, developing some small Python codes for solving some problems, right? Some easy problems. Then you can also suggest whatever you want from these sessions. So you can post your suggestions in the Q&A, and you can also post in the chat box of this Teams. So you can do that. Then, yes. So the agenda for today is, so we'll start with a motivation and introduction to the course. Assuming that you already, it's fine. The first week of the course is also introductory. It doesn't have, it is not too rigorous. It's just about why do you need nonlinear, when do nonlinear situations arise in structural mechanics, and why do you need them? Then we'll talk about linear systems. What makes it linear? What makes a mechanical system linear? So in mechanics, what constitutes a linear system? And what are the kinds of nonlinearity that can arise? And how do you characterize them? What are the different types? How do you classify them and solve different nonlinear problems? And I'll do an illustrative problem. So maybe 1 or 2 illustrative problems will carry it. So yes. So let us start. So the course name is Computational Continuum Mechanics. So it has got these 3 parts: computational, continuum mechanics. So computational, as you know, it has got to do something with doing computations. So this is basically, you have some numerical implementations. Computations, some things that you solve for. And continuum is the basic structure, is a basic uh, you can say assumption over which a lot of things are placed. And mechanics, as you know, mechanics is the study of all force systems and things like that. So given any physical system, let me explain this with a physical system itself. So I'm not sure some of you. So I know only one of your backgrounds, but it's okay. So let me. Recording is still on. Yeah. Let us suppose we have a truss, right? You have a truss member. So this example will be carried out throughout. So let us assume you have a truss member. Say you have an angle member. So this is an example from civil structural engineering, and we can also have it. We can also have relevant examples from mechanical. So yeah, that is the reason I asked your backgrounds. So these this is connected to a certain gusset plate. So this is what we call as a gusset plate. And the same on the other side. So you have a gusset plate here, which helps in transferring the load. And some kind of loading is applied here. It could be from a structure it is supporting, it could be anything like that. So there is some kind of forcing that is applied onto this. So this is what we call a physical system. Right? So the physical system has got certain members. So this is a um, metallic angle section, and here you have certain bolts. So this has holes at the end, and you put in bolts, you connect it with a gusset plate, and you apply certain forces. So this is a very well-defined physical system. So this can be realized physically. You give this drawing to someone, people can build this up. So this is a physical system. Now, for analysis, we usually make assumptions to get to a mathematical model. Right? We want to be able to get some predictive power. For example, something that is of engineering interest is that at what force will this, okay, I'm getting some background. Okay. Okay. Aman, Sony, maybe you have something to tell? I'm getting some voice from your.
No. There is nothing to tell.
Oh, okay. Thank you. Yeah. So this one is a physical system. This can be realized by an engineer. But for analysis, so we seek predictive power, right? We want to be able to predict certain things. For example, something that is of engineering interest is at what load. So suppose the total load here is some P. At what is the load? What is the load P at which this one fails, this one buckles, or it fails by some mode. So that is what we are interested in. So but this is a very you can say it's a complicated physical system. It has got two plates. It has got some 4 bolts and holes and this. So it's a pretty complicated physical system. But in order to be able to do computations, we construct simplified mathematical models. So as all of you know, how do you represent a truss member? You just represent it by a line connecting 2 points. A line connecting 2 points. And at the ends, you provide some kinds of support conditions. So so this is the first step. From a physical system, you get to what is called an idealization. So the physical system is the full description. And in getting from here to here, it requires some work. What is that work? It requires assumptions. So the assumptions are always guided by the observable. So it is always guided by the observations. Observations in by experiments, right? You can see if a so what kinds of so observations guide someone in making these assumptions. So what kinds of assumptions take you from here to here? So yeah, let's have it interactive. Uh, can you list a few that immediately comes to your mind, which takes it from a 3-dimensional assembly of bodies to a line in a plane connecting 2 points? What kind of assumption is there? First one, can you think of anything? Let us start with the member itself, right? From a 3-dimensional, so the member looks something like this, right? So it's a 3-dimensional body. Say it is an L section. It is going into the plane. So from this, you're going to a line. So what allows you to do that? First, can you suggest an assumption? What kind of assumption helps you do that? Okay, let me tell you. That is so the yes.
The material is homogeneous.
Okay, yeah, good. That's a very good assumption. So material is homogeneous, but that is still about the material, right? So that's a very good.
We have
Yes.
to
Yes.
consider that we will neglect the effect of a three-dimensional deformation.
Yes. So can you put it in a more concrete form? So this, what is a possible three-dimensional deformation for this? So this, if this is
Uh,
the cross section, this is a possible three-dimensional deformation, right? We neglect
yeah,
all these modes of deformation. That's a very good point. We allow deformation only in one direction. So the first point is very good. It is homogeneous. Since it is homogeneous, you're able to call. So first you're assigning a material property to this, right? In reality, it is made up of grains everywhere, and every grain has its own property. But at the scale, you assume it to be homogeneous. That's a good assumption. Therefore, you can assume something like E and nu. But in getting to E and nu, you assume something else also. Apart from homogeneous, you also say it is isotropic, right?
isotropic. Yeah.
Yes. So it's homogeneous, it's isotropic, and so if, let us put, so for the first, so one point is material, right? Or whatever she said is regarding material. What you said is regarding structural behavior. In in material, we have the assumptions of homogeneity. So what is homogeneity? I think it was a question in the assignment 0. So homogeneity basically means the properties don't properties are spatially do not depend on the spatial coordinates. So whether you take a point here or a point here, the stress strain response is the same. So properties don't depend on the space. And isotropy. So it is isotropic. Sorry, homogeneity is this. Then the second thing is isotropic. So isotropy is the properties at a given point do not depend on the direction. So at this point, whether you apply stress this way or this way, this equivalent strains are the same. So the uh, yeah, so you the material doesn't have its own direction. It's not like a composite. Say if you have fibers this way, the response in this direction will be different from the response in this direction. Unlike that, this is a homogeneous and isotropic material. Yes, that's a good assumption. Then you can also assume linear elastic. This is a very strong assumption, right? You call so this is where you assume something really strong. You assume the material is linear elastic, which means the stresses and strains are related by a linear relationship. Anyway, I was going to get to that in a future slide, but let us get, since this has come up already, let us start it right away. So let me also make this blank. Yes. So what is linearity? Right. So I said the material is linear elastic. So I made a statement: material is linear elastic. Material response is linear elastic. Let us split it up. So linear is something, elastic is something. So what is elastic and what is linear? One of them, okay, let me put it this way. Uh, so these are two different things. One of them is a mathematical idea. The other is a materials idea. So linear is something mathematical, elastic is something material, right? So let us see what is linear mathematically. So if you have looked at the two lectures, you will know linearity is with respect to some arguments of a function. You don't need to worry about what the function is. So treat the function as a black box. Let us say the function is f, and the function takes an input x and returns an output y, which is equal to f of x. So this x can be a vector, it can be a matrix, it can be anything. It can be a set of forces, it can be anything. So don't just think of scalars. You just function is something that maps one element to another element, right? So if you take the set definition of function, you have something's elements here, you have an elements here. Something that takes elements here and returns elements in this set is a function, and that has to be whatever. It has to be a single valued, right? It has to be single valued. So think of function in that sense. It's not a scalar valued real function or anything. You give some input, it gives an output. When the relationship between this output and input is linear, you call the function as linear. But what itself is linear? So linearity means if you give an input x1 and it returns an output y1, and if you give an input x2 and returns an input y2, f of, if you give it, so these two are conditions. So these are if this happens, if you input x1 and you get y1, if you input x2 and you get y2, which means y1 is equal to f of x1, y2 is equal to f of x2. If y1 equal to f of x1 and y2 equal to f of x2, then f of x1 plus x2 should be equal to f of x1 plus f of x2. Basically, in mechanics, you have a name, not just in mechanics, both in math and mechanics, you have a name for this. What is this? This is x1 is an input, f of x1 is its output, x2 is an input, f of x2 is its output. When you add the inputs, the outputs get individually added. So it has a good name.
Linear dependency.
Linear dependence is something else. Linear dependence is if you say x1, linear dependence is something else. Linear dependence is for a set of numbers or set of vectors, right? You just say one is a scale, one can be expressed as a linear combination of the others. That is linearly dependent, right? So if you have some elements A, B, C, etc., if you can express C as some linear combination, say alpha 1 A plus alpha 2 B, then you say C, A, B are linearly dependent. They are not independent. So here we are not talking about dependence. So the name starts with S if you require a hint, right? And the second letter is U.
Superimposition.
Superposition, right? So for linear systems, superposition holds. So this, yeah. So the more general definition that sir would have told in the lecture is if x1, if y equal to f of x1 and y1 equal to f of x1 and y2 is equal to f of x2, f of alpha x1 plus beta x2 is equal to alpha times f of x1 plus beta times f of x2 for all vectors or vector whatever for all inputs x1 and x2 and scalars alpha and beta. So in physics, so let us solve a small problem with it. Let me tell you that there is a cantilever with a tip load. Apply a tip load of x1. Yeah, this is fine. Actually, this is good enough. Let us say you have a system A, right? You have a cantilever and you're applying a tip load x1. And you have and the system B is that you have a moment here. Let us call it x2. Or rather, let me make it this way. Let's make a more interesting problem. So this is a trivial problem. I think you will be able to do it. Let us say you have a simply supported beam, right? You have a simply supported beam, and we have loading on. You have a loading like this. Right? Now, suppose, let me tell you the total. Suppose we don't have, so here the idea is not to solve structural analysis problems. Here the idea is to look at the concept of linearity. Suppose we have the solution for this, right? Suppose we have the solution for this. Let us say this. Let us call this load W. Let us call this. Now here the W is distributed throughout the beam. Here it is distributed only over half the span. Now suppose I give you the mid-span deflection due to this W is yeah. So suppose this results in a mid-span deflection of delta, right? Now, can you find what will be the midspan deflection in this case? Yeah, so here the maximum will be somewhere else, not at the midspan, but at midspan you will have some deflection. So let us use only the ideas of linearity. Okay, don't worry about how we solve for this. I'm giving you the when the full beam is loaded, the midspan deflection is delta, and I'm just asking what is the deflection here. Let us call what is the deflection here, right? This is the question. Sorry.
Del by 2.
Yeah.
Delta by 2.
Yeah, that is correct. And how do you get it? We want so this we know it is 5 by 3384 or something. But using the concepts of linearity, let us just look at the problem once again. Now, how do we construct this full load? So this full load is equal to this one plus this one, right? So so this let us call it as x1. This loading is this system is x1. This is x2. And we assume everything linear, elastic, isotropic, small deformations, small rotations, and material is linear and so on. So material is linear, elastic, isotropic, and the deformation is small. So these are the assumptions and beam theory holds. So these are the assumptions. So under these conditions, so we are actually interested. So we know that f of x1 plus x2 is equal to delta. This is what I'm giving you, right? Giving you f of x1 plus x2 is equal to delta. So here, let me put it this way. So the input is some kind of loading. And that loading is not really a scalar. It is you can think of it as a vector. So if you look at every point of the beam, at every point of the beam, we have a small loading, a small infinitesimal loading. And that you can call it as that entire configuration, you can call it as x1. Don't worry about. So this loading is x1, this loading is x2, and the output is midspan deflection. So the output is a scalar, right? So this is going to be a real number, and this loading is something. Now, so I'm giving that f of x1 plus x2 is equal to delta. And I'm giving you that f is a linear function or linear operator, whatever it is. Given the loads, the system is linear, it is linear elastic, so we get this thing. Now, so do you have an argument how you said it is delta by 2? So this is not the same as this, right? Do you have an argument how it is delta by 2?
Yes, sir, only it's a vertical loading, sir.
Yes,
So
it is vertical loading.
So it doesn't make a difference between a roller and a hinge here.
Yes,
So,
perfect.
So it is delta by 2, sir. By superposition principle.
Yeah, you're right, but it's the best. The good thing is, it doesn't make a difference between. Yes.
Here the relation between the output deflection and the loading is linear actually.
Yes.
So using that, if we consider that this UDL is acted on L by 2, and for the second case, this is L. This is on L.
Okay.
Then obviously the deflection will be the half.
Okay. Okay. So this is understandable, but both of you missed out. This is correct. So both of you had valid points. You said one of you said this. There is no difference between this roller and this because there's no horizontal force, which means there is no this horizontal force is 0 here. That's right. So it's like both are rollers. But what does that mean? And you said that there is linearity. So we can superpose the two. And hence the resultant is equal to delta. So individually, one of them should be delta by 2. That is your argument. But suppose if I ask the same question, same thing, if I ask this, will you be able to tell? You will not be able to tell, right? Suppose 3/4 of the span is loaded. You will not be able to tell the answer. So what is the critical thing that you're missing out here? So Dharani was actually a little closer. So since you said both are rollers, Can you tell something about this? If you flip it about the center line, what do you get?
Symmetric.
Symmetry, right? Perfect. So this is a symmetric structure. So whether you load the left half or the right half, you don't expect any. If you flip this, you will get this, right? If you flip this structure, you get this structure. So suppose this has a different delta in the middle and this has a different delta in the middle. If you flip, there will be a mismatch in the center, right? So since there is symmetry, this x1 is actually equal to x2. Sorry, not x1 is not equal to x2. x1 and x2 are two different situations. But since the structure is symmetric, f of x1 is actually equal to f of x2. But that cannot be said about any other point. So I should be very careful. You have symmetry. You have one half of the span loaded here. This is the point of interest is lying along the line of symmetry. So suppose for x1 this has delta 1, and for x2 loading, this is also the line of symmetry. So for x2 loading, it has a deflection delta 2. This is fine. If you flip this structure about the axis of symmetry, you should recover this, which means delta 1 is equal to delta 2. But what is delta 1? Delta 1 is f of x1. Delta 2 is f of x2. Now use the definition of linearity. F of x1 plus f of x2 is what? Delta. So it is f of x1 plus f of x2, which is equal to delta. But these two are identical, which means f of x1, 2f of x1 is equal to delta. So this gives you the result, it is delta by 2. So this argument of symmetry is very powerful. Right, sorry, symmetry and linearity. So let us go to this point. Yeah. So we were here. So structural behavior, there's an assumption. On the material, there's an assumption. And anything else? Do you have any other assumption here? What does it mean when you put two dots at the ends? We have what kind of boundary conditions are there here?
Fixed.
Fixed? Do you mean it's like this, moment resisting? Okay, you can. Okay, I can tell that that's a little ambiguous. It's so if these are bolted holes, and these will allow rotation. So bolted connections typically allow rotations. For a moment resisting connection, you need to weld this, right? You need to stop it from rotating. So since I just have one line of bolts in the mid axis, it will allow certain rotation. So it's a good idealization would be this. You allow vertical displacement on one side, and yeah, because this is loaded, right? So we have some loading here. This is here it should allow some vertical displacement, and horizontally you can. So this kind of this is actually a very this idealization really depends on the actual field conditions, what kind of connections we have, and etc. So the third idealization is boundary conditions, support conditions, or boundary conditions. Right? You have idealizations about the material, structural behavior, boundary conditions, and you have one more. What is it? So material, we assume linear elastic and all. Structural behavior is one thing. Boundary conditions is one thing. Then you also have something about the geometry of deformation.
Geometric non-linearity, I think we will not consider in this.
Yes, usually we don't consider nonlinearity, but we'll see this in detail, right? These three are obvious. This is kind of implicit when we talk about the strain measures. So I'll also come to it because that's a part of today's discussion. That's a part of this. Right. So using some ideas, so from a physical system, which is a three-dimensional body, which is a collection of three-dimensional bodies, we have already gone to a line. Next thing is write down the governing equations of the. So this is an idealized system. This you have a line with some kind of loading and support conditions. Now we actually want to be able to have some predictive power, right? That was our initial goal. From here, we need to get to the governing equations. So we already made the assumptions and got this idealization. Now how do we go? So here we use mechanics, right? So coming to this. Yeah, here now this is also a good place to talk about the continuum assumption. I can do that. But rather, let us finish this problem. Okay, let us just get to the end of this, solve the problem, and let us see if we introduce nonlinearity, what happens. So, what kind of here? So to go from the idealization to let me have some. Yeah, getting to the mathematical model from idealization. It's a critical step. It's a very critical step. So here we have a line with some drawings, right? We have some support conditions and they have some meaning, right? So here, let us give some, let us say the Young's modulus is E, cross section is A, length is L, this angle is some theta, and then we are applying a force P. Anything else that is required? Yeah, that's enough. Going from here to here requires physical principles. So here, the first physical principle we use is, so this is in static equilibrium, right? This is in static equilibrium. That is one condition. The second thing is, how are stresses and strains related? So we need constitutive relationships. And the third thing is compatibility. So any problem in mechanics, yeah, I repeat it in most of my, wherever I do this, any problem in mechanics, whether it is 3D or 2D, doesn't matter. These three forms the foundation of any problem in mechanics, in solid mechanics. So these three have to be respected regardless of whatever. Equilibrium, if it is static, it has to obey the equations of static equilibrium, which is the sum of all forces is 0, the sum of all moments is 0. If it is a dynamic problem, you need to satisfy the equations of motion, which is the sum of all forces is equal to the rate of change of rate of change of linear momentum, and the sum of all moments is equal to the rate of change of angular momentum, right? So these are the dynamic equations of motion, and these are the static equations of equilibrium. These have to be satisfied. Now here, that is one thing, right? That is one thing. There's the other thing is compatibility. Here, compatibility is not a big issue. Yeah, compatibility is one thing, which means the structure stays intact. You don't have mismatches. Say, suppose this bar extends by some amount. It should not violate this condition of roller support here. So that is one compatibility for this. And constitutive relation, we'll come to it, right? So constitutive relations are defined at a material point. Now, what is a material point? You have a solid like this. Look at the 3D view. You have a solid like this. At every point of the solid, you can apply some stresses and strains. So, can one of you recollect how do you define stress? Anything, it's okay if you're
limit delay tending to 0 del f by del a.
perfect. This is one component of stress, but that is okay. In 3D, you have other components, but this is a perfect definition. So mathematically, it is like this is a mathematical definition, of course, since you have limits. Physically, what it means, you consider a body. If I have to define stress at a point, right? Force by area of a point doesn't make any sense because area of a point is 0. So you consider successive areas which are enclosing the point. So say you consider this area which is enclosing the point. find what is the total force on that area. Let us say it is the F1 by A1. This is area A1. Now consider another neighborhood of that point, which is smaller than A1. So you construct a sequence. On that area, suppose the total force is F2. Right? This is another ratio. So keep doing this process. Then take a smaller area, F3. The force on that area will be F3 divided by A3. Do this sequence indefinitely. So this sequence of numbers, this is one number. Say this will be 10.3. This may be some 10.1, and this may be some 10.05, and so on. So this sequence of numbers will converge. So finally, you'll have some Fn by An, right? So this may be something like 10.00001. So this sequence converges to 10, if you see, right? This sequence kind of converges to 10. So this limit of the sequence is called stress. So you keep considering smaller and smaller areas around a point and take the ratio of force by that area. The limit of the sequence, if it exists, is stress. Similarly, you for strains, right? So the engineering definition of strain, uniaxial strain, you take it as change in length by original length, right? This is okay. This is kind of an engineering definition, but this is the global. This is the average strain over the entire member. If you take the total length of the member and look at the change in its length and divide it by the original length, that's the average length throughout. But if you see the finite element plots, right? If you look at some of the finite element plots, you get a strain field. You get different colors, right? So you have some body subjected to some forces. You see the strains and stresses are very high here, and they are low somewhere else, which means strain is also a pointwise quantity. So one definition of strain that we can look at even in 1D is you take, so multi-dimensional strain definitions are little, you need to know the concept of tensors, which comes in the next week. So it's a week 2 content. So we'll look at it next week. But in 1D, what you can look at is you consider very small segments of the member. Say you take a small segment. So suppose you want the strain at this point P. Consider a small segment of that member. Let us call that small segment as some X. Okay. Consider a small segment of that member containing the point X and see how much this length changes. Let it change by some delta X. Now take the ratio delta X by X. So again, you can do the same process. Keep taking smaller and smaller segments which are enclosing the point. So you get a sequence of numbers, delta X1 by X1, delta X2 by X2, and so on, right? So you'll get a sequence of numbers. This can go, say, it can start from 0.0013 to 0.0011, and this may be something like 0.001, 0.00001. Sorry, xn by xn. And so this sequence converges to something like 0.001. So you call the strain at the point P as the limit of this sequence. As you take smaller and smaller segments of length which is enclosing the point, and you let that length to tend to 0, but it will actually never become to 0. The ratio, this ratio will reach, it will converge towards some limit. That limit is the strain at that point. So stress and strain are local definitions. So in continuum mechanics, there is an axiom of locality. So locality means the stress at a point depends only on the strain at that point. As for example, that is very obvious, right? We don't expect the stress here. So let us take 2 points, P and Q, which are separated by some distance. If you say the stress at P, it is a function only of the strain at P. You don't want, on physical grounds, this point doesn't communicate to this point by any means, right? It's not possible. It's not possible to transfer the information of strain at this point to this point. So as this is an assumption of locality. Sigma at P depends only on the strain at P, and sigma at Q depends only on the strain at Q. So this is an assumption of locality. There are certain non-local models for some advanced materials, but at the lowest length scale, things are always local. There is no reason why this point will get to know about the strains instantaneously about the strains at some other point. So locally, you say there is a relationship between the stress at the point P and a strain at the point P. There is some kind of relationship. So what is linearity? Linearity means these two are related by a linear relationship. So if we take epsilon 1 plus epsilon 2, sigma of epsilon 1 plus epsilon 2 is sigma of epsilon 1 plus sigma of epsilon 2. This is material is linear. If the material is linear, this is the condition. Now there are various ways to look at. So if you consider all the 9 components of strain and 9 components of stress, you can have various linear relationships. But we already made the assumption it is isotropic, and cross-sectional deformation is not allowed. So you just take it as the uniaxial. So let us just take it as proportional. So this is a scalar. This is a scalar. For two scalars, linear relationship is just proportionality. So sigma is proportional to E, and the proportionality constant is the Young's modulus. Right, but this is all in 1D. In 2D and 3D, things get more complicated, but this is enough for now. So the stress at a point is equal to the Young's modulus multiplied by strain at that point. That is what we have considered. Now, so we have fixed the constitutive relation, which is sigma is equal to E times epsilon. Now, static equilibrium, that is quite straightforward. That we don't have to write down. And compatibility, we just have to make sure that the resulting deformation at this point, let us call this as A and B. The resulting deformation at point B is only downwards, and there is no resulting deformation at point. The resulting displacement at the point B is only downwards, and the point A is fixed. So, sorry. So at this stage, do you have any doubts? This is all basics, right? It's just brushing up the basics. If you have any doubts, you can tell. Yeah. Now, so this is all fine, right? So until now, I have been very, very slow. It's okay. It's just an introductory session today. So no, so here we are actually using. So I hope you see what is happening, right? We started with something like this, and now we are slowly getting to mathematical relationships. So these are called governing equations. Now let us list the governing equations for this problem. So first thing, this bar has to be in equilibrium, right? This bar has to be in equilibrium. If you take a small segment of the bar, it is subjected to a stress sigma. The adjacent segment of the bar is subjected to a stress, say, sigma 2, say sigma 1 and sigma 2, right? This is a bar. I'm taking two segments next to each other. Let us call this segment 1 and this segment 2. It has to obey Newton's laws. So these two forces, these internal forces have to be equal and opposite. But this is sigma 2, this is sigma 1, which means sigma 1 has to be equal to sigma 2. And there is nothing special about these two sections. These are just two arbitrary sections next to each other. And you can generalize it throughout the rod. So throughout the rod, the stress is just constant, just sigma. So at every point of the rod, you have sigma is equal to E times epsilon. Right? So now we have two variables. Sigma is one variable, epsilon is one variable. Let us list the variables, and let's also, these are the variables. Let us keep listing the variables. So right now we have two unknowns and one equation. So we need more equations. How do we get more equations? So this is sigma. What is the total force in the rod? If the cross-section area is A,
Sigma times A.
sigma times A. So let me call the internal force in the rod as, so this may look very trivial, but when we get to nonlinear problems, this has to be followed systematically. So let us call the force in the rod as F. Right? Let us call the force in the rod as F, sorry. No, let us take tensile as tensile force. Right? Okay. So F is equal to sigma times A. Now we are introducing another symbol F. So we have three unknowns and two equations, which means we need more equations, right? So what other equation we can get? You people can list. What other equation can we get?
strain is change in length by original length.
Strain is change in length. So in nonlinear mechanics, this is not really valid. The strain measure you just said, this strain measure is not really valid, but it's okay. For starting, we can do that.
We have to use the compatibility equation.
Yes, correct. So we got two suggestions. One is the strain is change in length by original length. So let me call the change in length as delta L, and the original length is L. So now I have another symbol delta L. And you suggested we will use the compatibility equations. So what is the compatibility equations here for this? What is the compatibility here?
The 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 algebraic sum of
Hmm?
the net deformation of these two segments will be 0.
Algebraic sum of the net deformation of the
If this
which two
bar
segments? Yes,
means what you have taken, if this
yes,
1D bar that you have taken is along the length, if you have considered the stress, longitudinal stress,
yes,
then since this is constrained by these two hinges, then the
yes,
net longitudinal deformation
is
of
zero,
these
is it?
two is yes, yes.
Yes, yeah, that is okay if I put this as a hinge, but this is hinge with roller, right? When it comes down, this net elongation will actually change. So that is not really, yeah. Since you have a roller, say, take the extreme case of a highly nonlinear deformation, right? So let us say I'm pushing the force all the way from here till it becomes horizontal, right? So this total length has changed, right? You can see that the total length has changed from something L to something else. So the length change is not, because of course it has to be different because it's a right angle triangle. The hypotenuse has to be strictly greater than one of its sides. So length will change, right? So that is not really correct, but you're on the right track. You can, there is a constraint on the total length, but it is not that it is zero. It is it is something else. Let us see. Now suppose this
Um,
comes down by let us say it comes down by V. V is okay. Yeah, V is not a V symbol is not used. If it comes down by V, what is the deal then? Right? If it comes down by V, can we relate the two lengths here?
yes, the we,
Yes.
we can get the vertical deformation using this V.
Yes. So suppose I'm specifying V. This initial length is capital L. After deformation, it's or let us make the force upwards. That's better because I'm considering tensile as positive. Let us. It's horrible. Let me write it. Yeah. Why is it not erasing? Okay, fine. So let me draw another figure. So let us consider the force to be upwards. So this is the initial angle. It goes up. That is just, you can also do it with downward. It's not a problem. Just that it will be more consistent if you use upwards. So say it goes up by a distance V, and there is a force applied which is P. Uh, and this length originally is L. This length is L plus delta L. Now, so usually there is a strength of materials or in linear structural analysis, there is an assumption that you project it onto this and then you take the change in length and that can be related to delta V. That is, so V is the hypotenuse of this triangle, this small triangle. So, and if this angle is theta, after deformation, this angle remains approximately theta. So, which means this angle is 90 minus theta. So, V cos 90 minus theta is this delta L. So it means delta L is equal to V sine theta. That is the linearized approach. So if you linearize the geometry, delta L is equal to V sine theta is that is the thing. If you linearize it, but we are not linearizing here. Let us take it we want to look at the nonlinear things, right? So let us take the exact. Oh, this problem has started. Okay. Let me just close this and reopen it. Okay. This is a bug in PowerPoint. Why does it still show saving? 34. Yeah, it's better we start in a different. Yeah, so let us do it afresh. So instead of using the linear relation, we're going to use something else. Let us say it undergoes some very large deformation, so that the initial angle is theta and final angle is theta plus delta theta. So let us say theta and theta dash. This distance is v. This distance is v. This remains fixed. This can move only vertically. Now let us see the actual deformed length. So originally it has a length L. Finally it has a length L plus delta L. What is L plus delta L? Okay, leave it. What happened? Okay, so this is all gone. So I think it was epsilon is equal to delta L by L. And then so we had another symbol delta L. And what was the other thing we wrote?
F is equal to sigma times A, sir.
Yes, that's fine. Thanks. F is equal to sigma times A. And then we have F as another symbol. Yeah, this was okay. Now I made this figure. We have L plus delta L. We have L. These two can be really different. There's no linearity. There's no linearization. And the initial angle is some theta. Final angle is some theta dash. This is like this. This is moving. This is moving so much. Let this call this V. Now L plus delta L cos theta plus delta theta. What is this? This is equal to this length. Let us call this horizontal length as h. This is equal to h. And what is L cos theta? Yes, it's simple, right?
H, sir.
H. H. Now can we eliminate h? H is not really required. So you put L plus delta L cos of theta plus delta theta is equal to L cos theta. Now we can do some expansion. So you call it as L plus delta L. So this is one equation. We have two variables. Delta L is a variable, delta theta is a variable, and those two cannot be entirely different. So delta L and delta theta are not independent, right? If it extends by some amount, delta theta will also change. So L plus delta L cos theta plus delta theta, I can write it as cos theta cos delta theta minus sin theta sin delta theta is equal to L cos theta. So we can write it as L cos theta cos delta theta minus L sin theta sin delta theta plus delta L cos theta, delta L into the entire thing, cos of theta plus delta theta is equal to L cos theta. So can we eliminate something? Or this is fine. Have it as it is. Let us look at the vertical relations also. So L plus delta L sine theta is equal to what? L plus delta L sine theta is L sine theta plus V, right? We can write this. L plus delta L sine theta is L sine theta plus V. And L plus delta L cos theta is equal to L cos theta, right? Sorry, cos theta plus delta theta. Now we have two things, delta L and delta theta. Both are not independent, they are related. So let us get rid of delta L. Just divide these two. So you get, can divide this by this. So you get sine theta by cos of theta plus delta theta is equal to this thing. So L sine theta by L cos theta will be tan theta plus V by L cos theta. So note that theta is not a variable. Initial theta is fixed. We are starting from some angle. Delta theta is a variable. And V is a variable, right? So this is a geometric compatibility relation. For the full nonlinear problem, delta theta and V are related by this relationship. So we can rewrite this. Let me think about it. So this is the geometry. So in this rewritten in any form is the geometric compatibility relation. So here I'm putting a fourth relationship, which is this entire thing, sine theta by sine theta by cos theta plus delta theta is equal to V by L cos theta plus tan theta. Is this okay?
Yes.
Right?
In
Now have
in
you
the
introduced?
in the
Yes.
numerator,
Yes.
you have considered the sine theta. Is it
Okay.
correct, or it should be sine theta plus delta theta?
Yeah, you're right. That's perfect. It should be sine theta plus delta theta. I made a mistake here. So L plus delta L is this is fine. And here it should be sine theta plus delta theta. You're right. Yeah, that's what was fishy here. Thanks for the thing. So it is tan of theta plus delta theta is equal to tan theta plus V by L cos theta. Let's be careful. So this is L plus delta L sine theta plus delta theta is equal to L sine theta plus V. Okay, I think, yeah, this is correct. This is fine. Thanks. Yeah, this is the right compatibility. So this is actually sine theta plus delta theta. Okay, so yeah, so this is the full compatibility relationship. Now let us see what can be done. So if so this introduces another variable, which is delta theta. So you have 5 variables and 4 equations. You still need one more equation. What is it? The relationship between delta L and delta theta. I said those two are not independent, right? So you need another relationship. For that, so here we already have 2 equations. We divided that and we got this equation. So use any one of them. Say you can use this actually. Use this so that you get a relationship between delta L and theta. So let us rearrange this. So you get, let us divide both sides by L. You get 1 plus delta L by L, right? 1 plus delta L by L is equal to cos theta by cos theta plus delta theta. So cos theta by cos of theta plus delta theta. And so this is actually fine. So delta L by L is actually the strain. So or let it be. So this is another equation. Either this or this. You can use either of them, but anyway, you don't need this unwanted B, so this is fine. So delta L by L is equal to cos theta by cos of theta plus delta theta. So this is a mathematical model for this problem. So 5 equations, 1, 2, 3, 4, 5 unknowns. So therefore, this is closed. This is it closed. So wherever you have delta L by L is appearing only here. No, let me check. There is some. You have introduced V. Right? You have introduced V. You still need one more condition. So if you look at this original problem, you need a relationship between this P and V. So you take one of them as an unknown, and the other comes out as an output, right? So this is a structural system. You input V, you get P. You can think of it either this way or the opposite direction. So you either apply a certain force and see how much displacement, how much is this point B displacing, or you displace the point B and see how much force you need to apply to make the displacement happen. So either one of them is a so our goal should be find P as a function of V, right? That should be our goal. So let us do it, right? So we have, which means there is also another unknown. So we want either, if you consider V as an unknown, you need one more equation. If you consider P also, you need another equation. So we have 5 equations and 6 unknowns. And now what is that you have not used until this point? So this is constitutivity. This is strain displacement. This is just integrating over the section. This is fine. This is structural equation. These two are compatibility equations. What is it you have not used?
A static equilibrium condition.
Static equilibrium condition. So what is the static equilibrium condition? We have assumed at that point the force is F, right? So you just draw an force diagram. So here you have a horizontal reaction H, and at that point B, and you're applying a force P in the upward direction. So sorry, this force I took it as sigma positive, so F is tensile. And what angle is this? This angle is now you can answer. So this angle is what? Is it theta or theta plus delta theta? This is again an aspect of nonlinear mechanics. What is theta? Is it theta or theta plus delta theta? Where does the force act? Yes.
Theta, sir.
Okay. Why do you feel theta? Any reasoning?
Initial conditions, sir. Initially, it is theta.
Okay. Okay. Good. So yeah. So this is what you would expect, but actually it's incorrect. So in continuum mechanics or in solid mechanics in general, this you have to remember. Or rather make this analogy. Okay, you have said theta. Let me explain it to you why it cannot be theta, right? So let us consider a spring, a linear spring, nothing much. Okay, and you're applying a force F. Spring constant is K. Now, what is the relationship between these two? Suppose this displaces by X. What's the relationship between F and X?
F is equal to minus kx.
F is equal to just Kx. X is in this direction, so it's just Kx. Right, if it moves to the right, you need a force F in the right direction, right? That's okay. It's just Kx. Yeah, the spring force itself is like this, right? On the spring, it is like this. So on the block, it is already in the negative direction. So F is just equal to Kx. Now, which means, so as you let X tend to 0, what happens? Force tends to 0, right? So, so where does the force act? Force acts after this has stretched by a distance, right?
Yes, sir. I
So
understood.
remember, yeah. So remember, all forces are in equilibrium in the deformed configuration only. Because this linear structural analysis is so common, we assume the undeformed and deformed configurations are very similar. We often think that the forces are all applied in the original configuration, but that's not correct. Forces always act in the deformed configurations. So the equilibrium has to be established in the deformed configuration. Right? This is a very important fundamental idea in its nonlinear mechanics. It is also fundamental in linear mechanics, but linear, whether you consider the uh, deformed or undeformed, doesn't make any big difference. Right? So plug in the charger. Yeah. Therefore, this angle has to be theta plus delta theta. This angle is theta plus delta theta. Now, can you relate F to P? It's simple, right? So F is equal to, or F result, F cos theta plus delta theta is equal to H. We are not interested in this, right? We are not interested in this. We only want P versus V. And F sine theta plus delta theta is P. So if either V or P is the thing, you have one more equation relating these two. So P is equal to F sine theta plus delta theta. Right? So you understand, right? You have to reduce this system of 6 equations to one equation between P and V. So V, you are taking it as input. P is an sorry. Either you take V as an input or P as an input. That doesn't matter. One of them is an input and the other is an output. So either V or P will appear here. Ultimately, you want to get a relationship between P and V. So either one of them is an unknown, other is known in terms of the other equations. So the task is now to eliminate all these sigma, E, epsilon, delta L, F, and then what else? Delta theta. So these are to be eliminated, right? Fine. So up to this point, we have come to the third step of this. So this is a big step. This is important. So from going from physical system to idealization, you just need assumptions which are guided by the physical observations on the field. So you see that the cross section is not deforming in its own plane, so you assume it is 1D. You see that the material is fairly homogeneous, isotropic, etc., and you assume it is the same in the model, and you idealize the support conditions in the same manner. In going from idealization to the governing equations, you invoke a lot of mechanics. You need the equilibrium, you need compatibility, and you need material model. Okay. After going to the governing equations, we'll solve it. Okay, with this can be solved in closed form. We'll do it, but that's mostly algebra. We'll do it a little later. From here, we go to discretization. What is discretization? This is a problem with just one member, right? So I'm pausing here just because this algebra will anyway come up in a later class. So we'll actually plot V versus P for a nonlinear spring, right? We'll do this. We'll actually solve this. But before that, let us get the flowchart completed. Okay. So from governing equations to discretization. So what is discretization and why do we need to discretize? So if you remember, somewhere in between, I had a slide on the continuum assumption. What is the continuum assumption? This is fundamental. This is again mechanics. Okay. So this problem was for a bar. But in general, you don't need 3D solids are not bars in general. That is for specific to that problem. So continuum assumption tends to unify a lot of mechanics. Let us see what it means. So Professor Sachin has mentioned in his slide. So continuum theory is like a grand unified theory in engineering science. So we'll see what it means. So let us take a potato-shaped body. Sorry. Let us take a body like this. And that body is acted upon by some forces. And it is heated by some kind of fire. There is some kind of energy input. And there is a temperature distribution, there is a displacement distribution and all, right? But if you take a closer look at what happens, what do you have in the body? Suppose it's just a pure metal. Say it is copper, right? Suppose say this is 1 gram of copper. Say it is 1 gram of copper. If you zoom in really, if you magnify really close to a material point, say call it. So I'm calling something called a material point. So this will also come later in the course. But right now, just take it as one speck of material, right? One small like dust particle of material. So this is called a material point. If you zoom in closely to a material point, if you keep on zooming in, what will you see? You'll start seeing atoms. So copper has got I'm not sure it's either FCC or BCC structure with. So let me model the atoms as spheres. And in between the atoms, there are attractive and repulsive forces. So in between the atoms, there are some kind of forces. So copper, the atoms are positively charged and there is an electron cloud. So the atoms are immersed in an electron cloud. So there are electrons running everywhere. And the interaction between these free electrons and the positive nuclei of copper, that puts them in, that gels them together. So that is the source of strength of these metals. So there is electrons running over all around. And these atoms are positively charged, so they attract those electrons. So these electrons are attracted by these atoms. So there is some kind of interaction. We don't need to get to that level. So right now there is some kind of atomic interaction between this. So this is copper, and say there is some kind of interaction. This is what it is. Now conceptually, if you think, we are talking about stress and strain at a point, right? Strain and stress at a point. We are also talking about displacement at a point. Same applies to temperature. Temperature at a point. Now, what do these physical quantities actually mean? You remember the limiting process I said, right? So you look at a material point, you consider volumes or areas enclosing it and keep taking smaller and smaller areas and look at the ratio of force delta F by delta A. It converges to some positive number. Not positive number, it converges to some number and you define that number as stress. But here what happens? Suppose that point is here. Beyond some point, if I take an area here, the force is 0. There is empty space, right? Atoms have a lot of empty space in between them. So in an empty space, the force is 0 and the area is, as you shrink the area, the limit remains 0. So what does it mean? If you shrink the point to lie on an atom, you have the force on the atom by the neighboring atoms, right? So if you shrink it to a point on the atom, you have infinite stress there because there is a force, and as you shrink it to the center of the atom, the area goes to 0. So atoms are discrete. Atoms are discrete entities. So on this atom, there are forces by other atoms, right? There are forces by other atoms. As you keep shrinking our volume to a point on the atom, there is a definite force. The force will not reduce any further because the surrounding atoms are all the same. But the volume will keep reducing, which means this limit does not exist as you shrink on an atom. And if you shrink this volume elsewhere, it is zero. The force is just zero. So how do we even deal with this sigma? Same applies to displacement. So we say that the displacement field of a point here, you say you talk about all kinds of displacement. A point is displacing and things like that. So you talk about a displacement u of x comma y or comma z, something like that. So if that atoms can displace, atoms are like particles. So here there can be a displacement. Here there can be a displacement. What does it mean to talk about displacement of an empty space, right? Similarly, temperature. If you talk about temperature, and classically, temperature is a measure of the average kinetic energy of atoms. So at any temperature T greater than 0 Kelvin, you know atoms keep vibrating at some frequency. And because of that vibration, you would have heat transfer. So the average kinetic energy of this vibrating atoms is some, I don't remember exactly. I hope it is some 3/2 Boltzmann constant times T, something like this. I may be wrong, but I know it is proportional to T. But but that is for a collection of atoms, right? What does it mean to define temperature at a point? But we talk about displacement field u of x comma y comma z, where there is empty space. You cannot talk about displacement of empty space. Similarly, temperature of x comma y comma z, you cannot talk about temperature of empty space. You need some material to talk about temperature. So what do these physical fields actually mean? That is where the continuum assumption comes into play. So this is also a part of, this is where a lot of so Newtonian mechanics is for particles. Newtonian mechanics, the Newton's laws, right? Newton's laws, if you recollect, say the first law states that a particle continues to be in its state of rest or motion along a straight line unless it is perturbed by an external force. So it's for a particle, and we are dealing with deformable solids. You cannot directly take it to a deformable solid. So Newton's laws of mechanics, Newton's laws of motion, are written for a particle. But physical systems are all something else, right? This is for a particle. Physical systems are all extended bodies. So the correct, if you see, strictly speaking, you have to apply the laws, you have to apply the Newton's laws to every atom here. So for example, you take the first atom and then say all the forces, sum of all forces on atom A is equal to the mass times acceleration of atom A. Similarly, the force, sum of all forces on atom B is equal to something like this. And the origin of these forces are coming from the Schrodinger's equation. So if you take 1 gram of copper, you have something like 10 power 22 atoms, which means, and for every atom, we have 3 components of displacement. So you have something in the order of 3 into 10 power 22 degrees of freedom for that. It is definitely unsolvable. This cannot be solved. Right? Such a large system of particles cannot be solved. But real bodies, this is just 1 gram of copper, and we are dealing with structures in the scale of meters and kilometers in the say bridges. What connects these two? There is something that connects these two, and that is precisely the continuum assumption. Continuum assumption. Right? This is the continuum assumption. And this is a very good assumption. So reality is this. Reality is we have atoms and we have displacements and temperature defined only at these points. But and if you have to really use the fundamental laws of physics, you have to apply it for all the particles. But we have so many particles, it is just impossible to model all of them. Not even 1 gram of copper. So you need some way to take Newton's laws and other laws from particle stage to extended bodies. What allows us is continuum assumption. What does the continuum assumption say? It states that so the fields are continuous. So when you define these quantities such as displacement, temperature, stress, and strains, you don't actually do it on the entire, you don't do it point-wise. You don't do it point-wise in a strictly mathematical sense. With every point, whatever you call as a point, you associate a small pocket of material, right? You associate so that's what it is. If you take this as a physical point, it can lie in an empty space, and all of these will become meaningless. Instead, you take a small region surrounding it, and you call that representative elemental volume or volume element. And the limit these limits you take not to the limit delta A tending to 0. You take it to the limit delta A tending to the limit A star, which is the area of this representative volume element. And you hope that this limit exists. The reason you hope this limit exists is that the physical scales are much higher than the atomistic scale. So this may be of the order of 10 power minus 15. And we are dealing with 10 power minus 3. So this is like 12 scales of 12 orders of magnitude higher. So much above this, the fields will be fairly continuous. So if you look at the displacement field, it will be something like here there is something, here there is some other displacement, here there is some other displacement, here there is some other displacement. Atoms will displace by some slightly different amounts. But these differences are in the order of this interatomic distance, right? But you are looking at millions and millions of such atoms. So you're looking at some body like this. So if you look at displacements like this, at this scale, they all are continuous functions. So the continuum assumption is that the displacement fields, all the fields are such that you can describe the displacement at any point, right? There are still atoms, but if you write down the displacement of every atom and things like that, they form you can express the displacements as a continuous field. You can express the displacements, temperature, stresses, strains as continuous functions of space. Actually, continuous functions in space and time of x, y, z, and t. This is a very strong assumption, and this holds good at engineering scales. At all the length scales that we are interested in, this continuum assumption is very good. If you go to outer space, right? If you go to the exosphere, if you go to some really, if you are say this is the Earth and you're going to the edge of the atmosphere, there the density is very low. So there at 1 meters, you may have something like very few molecules. You may have just 1,000 molecules in a meter cube in deep space. So in those regions, it's like the continuum assumption breaks down because there are very few molecules for the fields to vary in a continuous manner. So here the displacement will be something, some other particle will be say a few mms apart, and there the displacement will be something else. And you cannot fit a continuous function in between these two. Therefore, when the densities are really low, the densities are really low, or you look at length scales that are very close to the atomic length scale. Say you are looking at sub nanometer. Say you're looking at the scale of angstroms. There you cannot apply the continuum assumption. So basically, so this course name is computational continuum mechanics. Computation part comes here. Computation comes after continuum. The continuum assumption is that you can describe the displacements and other physical quantities by continuous functions. Yeah, that is the thing. Largely, you can describe the displacement fields and other physical quantities by continuous functions of space and time. If this is violated, entire continuum mechanics breaks down. Now, what has this achieved? The achievement is that if you have seen the lectures, it's one thing, it unifies solid mechanics and fluid mechanics. So continuum, the continuum structure unifies, we don't unify solid and fluid mechanics. It also unifies thermomechanics. So it unifies heat flow and solids and fluids in a very nice manner, but not gases. For gases, for the very reason, as I said, uh, gases are much have much lower density, right? Okay. Again, this problem. So gases have this low. Yeah. So gases have a low density. So that we may have very few molecules in a meter cube. So that cannot be treated as a continuum. So you cannot unify gas mechanics, but solids and fluids can be unified because there's a continuous flow of material, right? The material is a continuum. So no matter what, there are only 5 fundamental principles. One, conservation of mass. conservation of linear momentum, then conservation of angular momentum. So these are all coming from physics, right? Conservation of angular momentum. Then you have first law of thermodynamics. That is, energy has to be conserved. Then we have second law of thermodynamics. So these do not differentiate whether the material is solid or fluid. These are universally applicable. Thermodynamics. Yeah, we don't say it applies to gases because its kinetic theory is not still included. So this can apply to solids, fluids, stability problems, plasticity, elasticity, thermodynamics, heat flow, aeroelasticity, and so continuum basically unifies different areas of physics. Therefore, such areas where multiple physical things, say electrostatics, dynamics, magnetostatics, magnetodynamics, electromagnetism, uh, mechanics, solid mechanics, fluid mechanics, where all of these are put together is called, these problems are called multi-physics problems. Right? These are called multi-physics problems. Then, okay, so this is all fine. But so therefore, when you deal with continuous functions, when you deal with smooth functions, the conservation laws, these are the basic conservation laws, right? If you recollect, these are all differential equations. And when you apply it to a continuum, they all take the form of partial differential equations. Partial because you have 4 independent variables, x, y, z, and t. Here is where discretization is important. So you have physical systems represented by mathematical models, and these mathematical models make use of continuous functions. Continuous functions are you just have them everywhere. They are not discrete. You don't have a system of equations. Instead, you have a system of partial differential equations which are arising from these conservation laws. Now, from these to be able to solve partial differential equations are quite they're very you can have many families of partial differential equations, and it is not in general possible to get closed form solutions. There we make use of numerical methods. So mathematical models are usually, so in mechanics, if you remove the temperature part and you just look at mechanics of three-dimensional bodies, equilibrium equations are divergence of sigma is equal to so it is of some form. It involves the divergence of stress plus rho b is equal to the acceleration. And the compatibility has some other form. It is like curl of the strain tensor is equal to 0 for in the infinitesimal case. And material is an algebraic equation. Sigma is equal to some c times epsilon. So these are the so these all are in the for a continuum in 3D. They are all partial differential equations, and to be able to solve them, you need to discretize them. So you are going from PDEs to algebraic equations. Algebraic equations can be solved on computer, right? We want to be able to solve systems on computer. So from PDEs to algebraic equations, this process is called discretization. So these are called discretized algebraic equations. And what helps us go there is numerical methods. Or so you may be aware of various numerical methods in heat transfer and fluid mechanics. You use finite difference, finite volume method. And by far, the most popular method in solid mechanics, finite element. The finite element method. And in this course, computational continuum mechanics, most of these will be implemented by the finite element method. And once you get algebraic equation is nothing but Ax equal to B, right? Algebraic equation is nothing but Ax equal to B. You just solve them, So this is the full chain of processes that you have to take up while trying to model physical systems. Now we have closed this chain. Yeah. Any doubts? Did it go overboard? Was I too fast? Is it all okay? You can. Yeah. If you have any doubts, you can ask. If not, you can. I'll pause for a minute. You can tell if you have any issues. Any doubts regarding the assignments? Any other doubts from the lectures? Do you have any doubts? Is it all going good? Do you have any difficulty? You can tell me now.
Hello, Naresh. Sarvesh here.
Yes. Yes.
Um, yes. So, Naresh, I have some doubts in our zero-week assignment. In that, there is one question asking for the
Yes.
traction vector, and it's normal and it's a shear component. So, how to calculate that?
Okay.
So, I want to know that.
Okay. Let's go to.
Yeah.
Yeah. Is this the one? Yeah. Okay, so this requires a little. So have you had solid mechanics at graduate level or BTech level? That I can may know.
Yeah.
Hello.
That we didn't had that actually. Traction forces and all.
Okay, no problem. So this will be covered in an upcoming thing, but I can give you the procedure. So there is.
Okay.
So traction is something. Uh, so you have a solid body, right? You have a solid body. You cut the solid body at some. A solid body subjected to some forces. You make a cut here so that it will expose an internal surface. So the body will look something like this. And these forces are all gone. It's gone with the other body and you have some forces here. So these are external forces, but this body is in equilibrium. Every subsection has to be in equilibrium. So you have internal forces here. And now again, do the same limiting process. You take a point, look at successive volumes, so successive areas enclosing that point on this surface. Let us call this surface S. Look at successive areas enclosing that point and let that delta S tend to 0 or the representative volume. Right. Once you make the continuum assumption, it means even if you make it to 0, these forces are converging. So you get the limit delta F. So force is a vector. You take the limit delta F by delta S as delta S tends to, I'll put 0, but it is the understanding that it is the smallest volume you can get in the continuum. This is equal to the traction vector. Okay, so this, so traction vector at a point is the force intensity at that point. It's something like force per unit area or the force intensity at that point. So it's a vector. Now there's a good relationship. This comes later in the course, but the way to derive it is you consider a very small tetrahedron like this. Take a small tetrahedron and you expose a face like this. Say the tetrahedron has faces. Let me call this axis as 1 axis, 2 axis, and 3 axis. So opposite to 1, I'm calling this as ds1. Opposite to 2, I'm calling this face as ds2, and this face as ds3. And there is a face over. So this is a tetrahedron in 3D, and on this face, I'm having a traction t. It's a vector, and the normal to this face is like this. And so this is called the Cauchy tetrahedron analysis. Analysis, right? So the with the normal, yeah. So this is called the Cauchy tetrahedron analysis. It means you take a very small infinitesimal tetrahedron, you look at the force equilibrium of the tetrahedron. So this is the traction, and these are the other. So these faces will have some. So these faces are aligned with the coordinates, right? So what is sigma 11? It is. I hope this way you will know, right? Sigma 11 is what? It is the force. It is the force per unit area on the face perpendicular to axis 1 with in the direction So if you look at it, sigma 11 will be on this face in this direction. So this will be sigma 11, this will be sigma 12, this will be sigma 13. Similarly, this on this face it will be sigma 33. This will be sigma 31. This will be sigma 32. On this face it will be sigma. Sorry, this will be sigma 22. This will be sigma 23. This will be sigma 21. So this you can arrange in a matrix called the stress matrix or the stress. Actually, it's a matrix of components of the stress in this 1, 2, 3 coordinate system. So when you in the next week, sir will teach tensors. So the stress, the matrix of components is not the stress. Stress is a tensor. The matrix of components of the stress tensor at a given point along the 1, 2, 3 coordinate axis is the stress matrix that he has given here. This is the stress matrix. Now there is this Cauchy's relationship. So if you just establish equilibrium, so you have this is a three-dimensional body, right? It's an infinitesimal tetrahedron, but it is still three-dimensional. So you can write the three equations of equilibrium for this. So this traction, you can resolve this traction along the coordinate axis. So if you write it, you will get T1 is equal to so T1 acting on ds is equal to let me write it. It's hardly takes some time. So T1 acting on ds is equal to sigma 11 ds1 plus sigma 21 ds2 plus sigma 31 ds3. Now take ds to the other side, you get T11 is equal to sigma 11 ds1 by ds plus sigma 21 ds2 by ds. This will be done. Don't worry if you don't get it, if I'm too fast, ds3 by ds. And you can show that for the tetrahedron, this ds1 multiplied by the height is equal to the volume of the tetrahedron, right? The base into height. So that volume has to be the same. So you will have a relationship so that ds1 by ds is equal to the n1 component of this normal. So you have a face with normal n. The components of this normal vector along the coordinate axis are n1, n2, and n3. So this you can show that the volume of the tetrahedron is ds times n1 ds times the magnitude of the altitude of the tetrahedron, which is also equal to ds1 times dx1 and so on. So this will become this if you really, because there's no time, I'm skipping that, but you can show that T1 is equal to sigma 11 n1 plus sigma 21 n2 sigma 31 n3, and the stress tensor is symmetric, and you know that. So this similarly you'll get for the other two components of traction also. Finally, you can arrange it in a matrix form as sigma T1, T2, T3 is equal to sigma 11, sigma 21, sorry, sigma 12. Sigma 21 is equal to sigma 12, that you know, because of angular momentum conservation. Stress matrix is symmetric, 2, 3, sigma 1, 3, sigma 2, 3, sigma 3, 3. This multiplied by n1, n2, n3. You can check this. So sigma 11 multiplied by n1 plus sigma 12, which is sigma 21 multiplied by n2 plus sigma 31 multiplied by n3 is equal to T1. So all the three equations I have put it in a matrix form. So this is the traction vector. This is the stress tensor. This is the normal vector. Now, what are they telling in that question? If you see, they're saying now consider a plane normal, consider a plane normal to which makes equal acute angles with the coordinate axis. So it says that the plane makes there is a plane and the normal to that makes equal angles with all the axes. So what should the components of the normal be? In all the three axes, it should have equal components, right? In all the three axes, it will have equal components. So it will be something like 1, 1, 1. But this is not a unit vector, so divided by the magnitude of it. So it is square root of 3. So the normal to that plane is 1 by square root of 3, 1 by square root of 3, 1 by square root of 3. So this is the normal vector, right? This is the normal vector. Sigma is given. The sigma stress tensor is given. You have to find out the traction. So Up to this point, is it clear? So you have this image in mind. You have a plane. On this plane, you have a traction vector, which need not be normal. Normal is like this. Traction is like this.
Okay.
Using the normal, we can find this, right? So this traction, so just multiply. So whatever that stress tensor is, 10, 4, minus 50, 0, minus 5, 11. So this has to be symmetric. So minus 50, minus 5. This multiplied by normal. What is the normal? It is 1 by root 3, 1 by root 3, 1 by root 3. We take 1 by root 3 commonly out. So this will be 1, 1, and 1. Now just multiply this. So what is it? 10 plus 4 minus 15 is minus 1. 4, 0, minus 5 is minus 1. Minus 15, minus 5 is minus 20. Minus 20 plus 11 is minus 9. You have a 1 by root 3 outside. So this is the components of traction vector. Now they are asking the normal traction on hydrostatic component you can get. You just take hydrostatic and deviatoric, right? That you would have covered in BTech.
Yeah, yes, sir.
Yeah, hydrostatic is just
divided by 3.
trace diagonal sum of diagonal elements divided by 3. That you can get directly.
Yeah.
Now magnitude of normal traction vector on the given plane. So this traction you can resolve. So this is one axis, right? This is the normal axis. You can resolve it along so this will have a normal this normal looks very similar to let me make it slightly longer, or let me make the normal shorter. Let us call this as the normal, right? This is the normal direction. It is 1 by root 3, 1 by root 3, 1 by root 3. This is the normal, and this is the if you project this onto this, right? Say the included angle is some theta, right? This is the normal component, and this is the shear component, right? Normal is perpendicular to that plane, so the shear component has to be parallel to the plane. So this is the shear component. This is the normal component for this traction vector. So let us call it Ts and Tn. So what is Tn? Tn is equal to magnitude of T cos theta, right? You can also write this as magnitude of T, magnitude of N. Magnitude of N is 1 because you are normalized cos theta. And what is this? That's the dot product, T dot N. So we already got T. This is the traction vector. Dot product this with the normal component. So they're only asking the magnitude. So it is minus 1, minus 1, minus 9, 1 by root 3. Dot producted with 1 by root 3, 1, 1, 1. So 1 by root 3, 1 by 3 will be 1 by 3, and minus 1, minus 1, minus 9. So it is minus what, 11 by 3? Yeah, I'm not sure. Numbers I might have copied something wrong, but I hope you get the overall idea, right? So the magnitude of, so this Tn is equal to T cos theta, which is T magnitude of N cos theta. This is nothing but the dot product between T and N. So do the find out the traction vector, dot product with N, and then you get the normal component. Right, so this hint they are asking up to 2 decimal places. You can find out. So, any doubts here up to the normal component?
Yeah, no doubts.
It's okay, right? This only thing that I skipped here is how is this ds1 by ds equal to the normal? That it will be covered. It will anyway be covered. It will be done. And the shear component, so Tn square plus Ts square is equal to magnitude squared, right? Magnitude is whatever 1 square plus 1 square plus 9 square by 3 under root, whatever this is. And this is the right hand side. This it is some minus 11 by 3 square. So the shear component you will know. Yeah, they're asking the magnitude, so don't put the minus in the. So shear you can just subtract and get whatever this is. That is the next shear component thing. And the last thing is magnitude of traction vector that you already found out. That is this. That's clear. Right? Is that okay?
Thank you, sir.
Anyway, yeah.
Thanks.
Yeah. Yeah. For this week's this is I think all of you will be able to do it because the questions are directly from the slides. So yeah, I didn't finish that trust problem. We'll solve it. So this interdisciplinary area I just said in the and for a linear system, if the input is doubled, the output is that you will be able to do. What needs to be linear? Yeah, that you can do. Yeah, I think we are at the end
So
of time. Anyway,
each
yes,
and every
Yes.
week
Naresh, can
we will.
you?
yes.
Hello.
Maybe one by one. Yes.
Yes. So, Naresh, can you explain the last question? That is the material nonlinearity is handled in a kinematic and a material nonlinearity.
Okay. Okay. Material nonlinearity is handled globally while the
Yeah.
kinematic. Okay, I cannot tell the answer because I'm not supposed to tell, but I can explain the concepts of material and kinematic nonlinearity. Okay, that is one
Okay.
thing. And Aman, you were telling something. I'll just take his.
No, actually, I want to know whether this problem solving session each and every week we will get the same time, or it can be changed also.
It is the same time. We have given the 6 to 8. So they asked
Okay.
me which time will be comfortable. So it's Mondays 6 to 8.
Okay.
Yeah. You can actually you can even post your questions beforehand if you have any, and we can
No,
discuss them.
actually, why I'm asking because uh, when today when I was in my office, so the off time of my office is 5:50 actually, and
Oh, okay.
I did a very hurry up to join the session.
Okay.
Means I have ride my bike with the over limit speed.
Okay. So
Uh,
maybe I will. Then we'll do one thing from the next sessions. If there are questions, I'll take the other questions in the first, say, half an hour or so. Then we'll get to the problems in the later,
okay.
so that you can join. And even if you, anyway, the recordings will be available. You join at your convenience. Even if it is half an hour late or so, it's fine. You join at your convenience. The recordings will be available. You can watch the recordings and you can post the question in that forum, or you can also email it to me. I have given my email address, right? This nareshc@IISc. Yeah, you can also email it to me. I'll respond within a day, and then yeah, because changing it means NPTEL will have to push it to. Uh, they'll have to email all the people again, and I will also have something else to do in the daytime. That is the reason.
And do you have any industry experience also?
No. I joined directly after my BTech. I don't have any industrial experience.
Okay. Okay.
Okay. Okay. Thanks for attending. I'll just clarify that question. So we said there are. Okay, we didn't get to that point, but I'll. Yeah. So linear system, we saw that everything has to be linear, right? The linear. Yeah. So in a linear system, if you give input x1, x2, you need everything to be linear. Sorry, you get f of x1 plus f of x2. This is linear system. And in a solid mechanics problem, you saw that equilibrium, uh, stress strain relation, which we call constitutivity, and compatibility or strain displacement relation. Right? These are the key things. So once you for the trust problem, we wanted to get a relationship between P and V. So suppose I input V, I want to get out P using all these three relationships, right? So these all will take the form of partial differential equations. Plus, you will have boundary conditions. So these I just already listed the equilibrium equations, stress strain, and so on. This is algebraic. This is a PDE. This is a differential relationship. Plus, we have the boundary conditions. Boundary conditions are like force and displacement boundary conditions. Now, if this input P and the output P has to be linearly related, all these intermediate steps have to be linearly related. So you input the forces and you have stresses here. And from stresses, you have the strains. And from strains, you get the displacements. And from displacements, you get displacement. This is displacement everywhere. And from there, you get some boundary displacement, or say applied or displacements of interest. Displacement at boundary. Forces are also like that. Usually forces are at boundary. So from boundary, this is the bulk. This is bulk. This is at the boundary. So these two, so it's like you have a body here, you apply a force here, we have some kind of displacement boundary conditions, and you have boundary displacements. So this force, if I double this force, say if I apply P, I want to get V. If I apply P into 2, I should get V into 2. This is the linearity that we're looking for. When this linearity can break down, when any of these linking arrows are nonlinear. So everywhere in between, there is a black box, right? This black box is the material stress strain relation. This black box is the strain displacement relation. This black box is displacement boundary conditions. So this black box is the material black box. And when the relationship between stress and strain is nonlinear, we call it as material nonlinearity. And as I already told you, stress strain relationships are local, right? You have the stress at a point, that's a locality assumption in continuum mechanics. The stress at a point depends only on the strains at that point. But for displacements, it is not the case. The displacement at this point also depends on the forces at this point. So displacements and forces are global quantities. There is no locality assumption in continuum mechanics for this. It should not be, right? If you have a force here, this will obviously deform. Say, if this is fixed and you apply a force here, this will bend and this will obviously deform to some point here. So these two, they are globally related, and stresses and strain displacement relation. These are also strains at a point, strains at a point are related directly only to the displacement at that point. So you will see what the strain displacement relations are. For example, it is like the delta L by L in that case. It's like only at that. So the strain in that member cannot depend on delta L by L of some other member. It's like that. But it will become clearer when he does the 3D part. So this is also local. It could be nonlinear, whether it is linear or nonlinear. So this gives rise to geometric nonlinearity. This gives rise to geometric nonlinearity. Now we said, so we have stresses, stress-strain relationship gives rise to material nonlinearity. Strain displacement relation gives rise to geometric nonlinearity. And we also said there are some boundary conditions which are relating the global quantities to the local quantities. What are these boundary quantities? So these are boundary conditions. So boundary conditions could be linear or nonlinear. And when they are linear, when they are nonlinear, this is called the kinematic nonlinearity. So now you can take a look at that question once again. So you have this material nonlinearity is handled globally, whereas the kinematic nonlinearity is handled locally. So you might have already got the answer, but I cannot tell that. But you know where the material nonlinearity exists. This is all in the bulk, and stress is at a point, strain is at a point. So these two are locally related, whereas forces and displacements are globally related. As an example, you can look at this one simple example. Let's not get into the complicated ones. You have a mass, or no need of a mass, you just have some rigid block. You have a spring constant K, and you have another wall here, right? you're applying a force F. So this is a nonlinear problem for some reasons, right? So if this wall is not there, say this wall is not there, you have F equal to Kx, where x is the displacement. And if it's a linear spring, if K is a constant, you get a linear relationship like this. But you have a wall here. So let us call this distance as some finite delta. So if x is less than delta, there is no problem. The boundary condition is F is equal to Kx. If can x be greater than delta? Can the displacement of this point be greater than delta? No, right? You have a wall here. Yeah. So if you, the other condition is x is equal to delta. If x is less than delta, F is equal to Kx. If x is equal to delta, what is the force? Force in the spring is so let us call this force as Fs. Again, if you recollect what sir said, you always have the equations are F internal is equal to F external, right? F internal in this case is Fs, and that is equal to Kx if x is less than delta, and it is K delta if x is equal to delta. What about the external forces? External forces are when there is no contact between the two. At this point, if you draw equilibrium, here you have F and here you have Fs. So using the equilibrium equations, F is equal to Fs when x is less than delta. Once this has touched the bar, right? Once this touches the bar, you will start getting, touches the wall, you will start getting normal forces from the wall. So we'll have a normal force N. How much is the normal force? It could be anything, could be very high. So in that case, F is equal to Fs plus N. How much is the N? So you apply a certain force. If you say X is the solution, if you plot X versus F, initially it will be linear. Once X reaches delta, force will become force in the spring will be K delta. And if the total force is F, the normal force is just F minus Fs, right? So you can have as high a normal force as you want. So this is rigid. So this can take any amount of force. So as you increase the force, the displacement will remain constant. So the force displacement response will be like this. Force can even go to infinity. So this is a kinematic nonlinearity. Why? The boundary condition. If you look at the boundary condition, you have something like this. A boundary condition itself is unknown. So the boundary conditions are F is equal to Kx if, or leave Kx. Kx is actually a constitutivity. F is equal to Fs if x is less than delta, and x is equal to, otherwise x is equal to delta and F is indeterminate. So this is the boundary condition. The boundary condition is a mixture of kinematic specifications such as x equal to delta and F equal to Fs. So how do you actually solve for the problem? We are only applying a force. We don't know how much x is, but the boundary condition itself depends on the solution x, which we don't know before solving the problem. So this is kind of global, right? You don't deal. So you can also replace this with a rod, right? Nothing changes. You can replace it with a rod of E, A, and L. And at every material point, you have material nonlinearity. You can have material nonlinearity at every material point. But the boundary condition is a kinematic nonlinearity. You are specifying the boundary condition, which itself depends on the solution. That's why instead of getting a linear thing, if if there is a force F that causes 0.6 delta, if you multiply F by 2, you will not have the displacement as 1.2 delta. That is incompatible. So you have an inequality constraint that X is always less than or equal to delta. Whenever you have inequality or equality constraint, that is a rough nonlinearity. That's a kinematic nonlinearity, and you see it is not a local thing. It depends on everything else. You solve for the entire system, and then you look at whether the constraint is satisfied or not. Yeah, that is how you solve it. You solve the entire system. You see if you take a trial solution, you see whether x is exceeding delta. If x is exceeding delta, then x is equal to set x equal to delta and find the force, whatever force you're applying on the normal force. If x is not exceeding the delta, you're doing something. So you're globally solving the problem once, looking at the solution, if it is satisfying the inequality constraint. Yeah, so this is a kinematic inequality. That is, this is how it is solved. So I think you get the answer, right? Material, you do it locally at every point. Globally doesn't matter. And kinematic inequality is kinematic constraint is satisfied in this fashion. Is that okay? You get the answer?
Yes, Naresh. Yeah.
Yes. Yeah, I can ask if there are any other doubts, and no more doubts, I can stop recording and
No,
yes.
right now I'm not having anything.
Okay.
So we can mail, if we are getting some difficulties in between while solving the
Yeah.
assignment at all.
Yeah, you can mail me. Anyway, next week will also be 6th, 5th, right? Yeah. Assignment deadline is anyway 7th. So even if you have any more doubts, you can ask.
Okay, fine.
Okay. Yeah.
Yeah.
Thank you.
And where
Thanks
will we
for
get this?
which one? The
Recording.
recording, I'll upload it onto this channel. Oh, I forgot to tell that. So there is this all my previous
Okay.
NPTEL things I uploaded here. You can search for this. NPTEL will actually make it available in the course page. So here usually there will be another. Did they put it already? No. Yeah, there'll be another tab here saying recordings, live
Okay.
sessions. So in that you
Okay.
can go click and access the things. But before that, if you wanted, you go just search for this Naresh Chockalingam Academic. You will get all the recordings. I'll make a playlist and upload it here for Continuum.
Okay, fine.
Okay.
Yeah.
Thank you.
Yeah. Thank you so much. Yes.
Yeah.
Yeah, bye.